Chapter 6, Section 4, Adding and Subtraction with Unlike Denominators. Well, we're going to add and subtract with least common denominators is the method. We talk about this a little bit at the beginning of the chapter about having to make sure the pieces are the same size. Like when you're adding 1/2 to 1/3, we'd have to change those to sixths. So we find the LCD, or least common denominator, between thirds and halves and so on. And they'll show some of this in the examples rather than me. I'll talk about it all the way through right now. And then we're going to talk about when factors are opposite. This manipulating negatives comes up quite a few times, and it's a very good tool. So they keep showing this that there's some ways to factor out or use -1 over -1, or basically multiply by 1 in a special way to set up fractions so we can add or subtract or do some other things too. So let's look at this. First rule is that to add or subtract a rational expression, a fractional expression. Another way to say it is for rational expressions is having different denominators. So now the lower part of the fraction is different. We're going to work with some things with the identity property and some stuff that we can do to create fractions with the same denominator. Well, they're going to go through these rules. I'd prefer to think about using multiplication by 1, and they kind of explain this here too. It says multiply each rational expression by the form of 1 made up of the factors of the LCD missing from the expression's denominator. 3. Add or subtract numerators as indicated. Write the sum or difference over the LCD. In other words, just to sum this up, make the denominators the same. Once I have the same denominator, then I just add or subtract those numerators. So look at example 1 here. It says add 5x squared over 8 plus 7x over 12. Well, they use prime factorization, and I think that's a very good thing to be focused in on, rather than, with 8 and 12, you might start thinking about, well, what can I could list multiples of 8 and multiples of 12 and very easily see that 24 is the common one that comes first, or that's the lowest one, right? And these are least common multiples we're using in a denominator, which is the least common denominator. But using prime factorization to find LCDs or LCMs is a very good tool, because when we get into expressions other than numbers, it gets a little harder to list multiples. So we're going to use prime factorization to find our LCD. Well, prime factorization of 8 is 2 times 2 times 2, or 2 to the third power. 12 is 2 times 2 times 3. Well, the LCD is all factors and don't repeat common ones. So we got 3 2's and another 3 here for the prime factors, which you multiply and you get 24. The denominator 8 must be multiplied by 3 in order to get 24, this LCD we figured out. Well, what we do is we multiply by 1 right here. So they're basically, first they rewrite this addition. They just write these as prime factored over prime factored. This is 8 and this is 12. And what is the missing prime factor to give me my LCD? Rather than, I could do that and I could say, well, 8 times 3 is 24. So I need to multiply the denominator by 3 to get 24. Well, the only number I can multiply by and not change the value of this fraction is 1, so I have to make a fraction of 3 over 3. And same thing here with, I have 12, I need to take 12 times 2 to get 24. The way they're explaining this and the way they're showing this works in all cases. We're kind of used to easy to kind of fall back to mathematics, but we want to stay in this algebra side of this deal. So What they're doing is picking out the missing prime factors that make up this LCD, 2 times 2 times 2 times 3. Well, this one has 2, 2, and 2. I need a 3. So I make a fraction with that missing prime factor, the same numerator and denominator, that's equal to 1. Well, here I got a 2, 2, and a 3. I'm missing a 2. And that's what they want you to see basically in this simpler example. So you multiply that out, I get 15x squared over 24 plus 14x over 24. And since I have the same denominator now, I just add the numerators. And then they still prime factor. When we're doing any of these complex rational expressions, I still need to make sure after I add or subtract if I'm in simplest form, or the only common factor or the largest common factor between the numerator and the denominator is 1. So they prime factor this. I look at this expression that I get up here on top. That is not prime because there's a common factor of x in both terms. So we factor that out. X is prime. That's 1 and x are the only factors of x. And this expression I cannot factor any other way. In other words, this is prime. 1 and this expression are the only factors. Well, 24 is not prime, but I can show that is really 2 times 2 times 2 times 3, which are prime factors. Hey, there's no common prime factors between the numerator and denominator. This expression is in simplest form. And that's what they say, cannot be simplified. Better way to say that, it is in simplest form. Definition is what I just explained. Okay, example 2 is subtraction. Now I have a little more, I got variables in my denominator, but the principle in the process that we go through is basically let's find LCDs by prime factoring. Well, 8x is 2 times 2 times 2 times x. 12x squared is 2 times 2 times 3 times x times x. To get the LCD, I represent all prime factors and not repeating the common ones. So I have a 2, a 2, a 2, a 3, an x, and an x. Okay? So we end up with this when we multiply this, the LCD is 24x squared. Now I wouldn't write it that way to begin with right here. I would say what are the missing prime factors from this one? What do I need to multiply to get to this prime factors multiplied? Well, I got a 2, 2, 2. I got 3 of the 2's taken care of. I need a 3 is not there, and I need an x. That's where they get this 3x. Well, I need only thing I can multiply by is 1 and not change the value of this fraction. Well, this other one here, 12x squared, 2 times 2 times 3 times x. And what's the missing prime factors? In this case, it's only 2. So I take it times 2 over 2. Very nice way and method to deal with leaving things in their prime factorization will make this what do I multiply thing work really easily. Very good way to do this, the way the book shows us. So I do the multiplications and I end up with these new fractions, 21x over 24x squared minus 10 over 24x squared. And this is a good caution. I see this all the time and I kind of I shouldn't laugh, but it's kind of like if you're trying to memorize process, why are we doing this? You need to think about why am I doing this? The goal of going through all this LCD stuff and prime factorization is to make sure I got the same denominator so I can, in this case, subtract the numerators, right? That's the only way I can do subtraction or addition of fractions. These denominators need to be the same. Because if you stop or the phone rings or you get a text message or something like that and you look at your work right now, you're going to say, oh, these are not in simplest form. And then you simplify it back to 7 over 8x and 5 over 12x squared, and you're back to starting all over again, right? Remember what you're doing here. I'm trying to get a common denominator so I can do the subtraction or addition. So now I go here and I say, well, now since I have these, I can just take 21x minus 10. Then I would check to make sure that I do have a fraction in simplest form. Well, factors of 21x are 3, 7, and x, right? I can look at it right here. Here's all the prime factors. 10 is 5 and 2. Okay? Well, I have no common factors between these two terms, so I can't factor out a common factor. You cannot say, hey, there's a 2 here and a 2 here. That does not work when there's a subtraction up there. It only works with factors, okay? So that fraction is in simplest form. Example 3. Now, they're just kind of stepping up the complexity. Not really any new principles here. We've been adding and subtracting fractions for a long time. You have to have that common denominator to do that. Well, these denominators just have a little more complex factoring because we've been doing that, and you should know how to do this stuff. So in example 3, we have 2a over a squared minus 1 plus 1 over a squared plus a. Well, to find the LCD, because they have different denominators, I have to find a way to get to common denominator is I prime factor those. Well, a squared minus 1 right here is difference of squares. That factors to be a minus 1 times a binomial here of a plus 1. Remember the strategies, and I kind of skipped that. What's the first thing when we factor? I look for common factors first. I don't have any common factors here. Then if it has two terms, then I look for difference of squares. And if it isn't difference of squares, I look for sum or differences of cubes could be there. And if it doesn't have those things, we're pretty much done as far as two-term factorization. Well, this is difference of squares. Well, the next one here as I start out, well, I look for common factors first. That's the easiest type of factoring. And there is a common a in both of these terms, so we factor that to be a times the quantity a plus 1. Well, the LCD, here's prime factor, here's a prime factor, prime factor, prime factor. I have 4 prime factors. I represent all prime factors and don't repeat commons. So I end up with a minus 1 times the quantity a minus a plus 1 times a. Now I would leave this. I could multiply this all out and end up with a to the 4th minus a, and, or excuse me, a to the 3rd. Sorry, I'm doing too much in my head there. But I would leave this prime factor because the prime factorization tells me what I need to multiply by. So when I'm trying to change this 2a over a squared minus 1, I already know that it's 2a over these two factors, that difference of squared factor. Well, what's the missing prime factor for the LCD? Well, it's got this one, it's got this one. It doesn't have the a. So I need to multiply the denominator by a, and the only way I can multiply by anything in here, it has to be equal to 1, so I make it a over a, which is equal to 1. Well, this next one I have this factored a squared plus a is a times the quantity a plus 1. Well, I got the a now, and I got the a plus 1. What's missing in my LCD is a minus 1, so I have to multiply that by a minus 1 over a minus 1. And that's kind of what they're telling you here on the side. So I do that multiplication, and I'd still leave it prime factored. These are exactly the same thing, just in a different order, which means that now I can put this addition over this prime factorization, or the LCD. And I end up with 2a squared plus a minus 1. Hey, that's a trinomial over these factors. So I need to find out if I'm in simplest form. So can I factor this trinomial? Well, first I look for common factors again. In this case, there's not a common factor for these terms. And then what? Well, I don't have a binomial, so I'm not looking for difference of squares or sum of cubes or difference of cubes. I have a trinomial. The first thing you should look for, do I have a perfect square trinomial, which is the first term has to be something squared and the last term. Well, neither one of these are something squared, so that's out. So what you end up doing is grouping or reverse FOIL, and I end up factoring this into 2a minus 1 times the quantity a plus 1. I leave this prime factored because I'm hoping, or if I need to simplify, it'll become obvious because I have the denominator and the numerator prime factored. Well, they have a common factor of a plus 1, which is equal to 1, so I can basically say this is the same as 2a minus 1 over the quantity a times the quantity a minus 1 times 1, right? Or just that. So you simplify that. I can't emphasize enough about how this work is done, because I see a lot of students will do this work, you'll get the right LCD, and then you'll multiply it out, and then you'll not recognize that you have a way to simplify that fraction when you get done. Example 4 is a subtraction. Now in this case, it's nice because the denominator and of both of these are prime. There's no way to factor x minus 2 or x plus 5. So how do I get, the next deal is here is they show the LCD is just the multiplication of those two. And this is the work where they show, well, the missing prime factor for this LCD is x plus 5 and the other one is x minus 2, so I multiply by 1 and I end up with these two trinomials over this same denominator now. So I can subtract these. Now be careful when I subtract something, remember that the fraction bar is like grouping symbols. So really what I'm doing is subtracting everything above in this numerator here. Or in other words, I take the opposite of an add, and that's what they show here. So this x squared goes to negative x squared, negative 9x goes to 9x, and 14 goes to negative 14. Which I think is a very good way to do that, is to try to stay in addition, in a sense. See, I would actually sometimes I'll write plus negative x squared and plus negative 14. And technically that's what you have to have is addition for change in order, because to combine like terms, I'm going to have to change the order of this, the commutative property, and change grouping, the associative property to be able to do things like, and the distributive property to combine like terms. Well, they do that, and you'll notice that x squared minus x squared is 0. I get 9x plus 9x is 18x. 20 plus negative 14 is 6. Notice they still left this prime factored, and then I factor this, which it has a common factor of 6, to be 6 times 3x plus 1, and then I make sure that there's no common factors here, so I could simplify in this case. There's not, so that fraction is in simplest form. And again, I'd leave it just like this. Don't go back to 18x plus 6 or anything else. Don't take extra steps, which increases your possibility of errors. So basically the same thing here. In this case with example B, they prime factor the denominators. Is it pretty obvious that it's the same process? And so what I need to remember to do these kinds of assignments is, first, the goal is to get a common denominator so I can do the addition or subtraction. Well, how do I do that? I can use prime factoring to do that. So I use prime factoring to get the LCD. So I'm going to be factoring denominators to start with, and then you're going to multiply by 1 in a special way to create new fractions with that common denominator that we've determined in this case is here, and then be careful about subtraction. Now in this case, after I do the subtraction, I end up with this trinomial of x squared minus x minus 6. Well, I can factor that again, and I factor that to be x plus 2 times quantity x minus 3. Hey, there's a common factor from this prime factorization of the LCD. There's a common factor that equals 1, so I end up with x minus 3 over x plus 3 plus over x plus 1. A lot of steps, a lot of work, nothing really new. This is not more complicated, I like to say. It's really just more complex. It means there's just more steps possible because we have more factoring and maybe more complex factoring, right? So hopefully you get the concepts around this idea. If you really focus in on that, you're going to have a lot less problems doing this on an ongoing basis. And hopefully you do those correctly, okay? The last part of this section is when factors are opposite. And again, I kind of explained that at the beginning of the section. If I want to change the sign of anything, I can multiply it by -1. In fact, multiplying by -1 is saying I want the opposite of that, or I want the sign change in this case. Well, I can do this with fractions as long as I multiply by 1. Now, I can make a fraction equal to 1 by going -1 over -1. So like in this case, I have 8a and -8a. I'm going like, wow, it'd be nice if I had a way to make these the same denominator. Now I could do the whole thing about prime factoring, list all factors, and that kind of stuff, where this would be 2 times 2 times 2 times a, and this would be -1 times 2 times 2 times 2 times a, and you could do that all and basically find a common LCD of a -8a, and then multiply by the missing ones, and it'll all work. This is really kind of a shortcut though. If I know I just need to change the sign of one of the denominators to make them the same, I can do this by multiplying by 1 using a -1 over -1. So that's what they do here. They say, well, wouldn't it be nice if I could change this -8a into 8a? So they take -1 times over -1 times this. Well, this changes this to a positive 8a. Hey, that's nice because now I have the same denominator. But it also changes the 1 on top to a -1. So now I can just add the numerators and get 2 over 8a. Now I can simplify that because there's a common factor of 2 between those two, and I write 1 over 4a. Now, the other thing, like just what I said, you could do everything the same, find the common denominator the same way by listing all the factors. In this case, -1 would be one of those factors, and then make sure both are a -8a is where we'd end up there, but you'd still end up with you'd end up with a -1 over -4a, which then we would expect to factor out that -1, and you'd end up with the same answer, just causing more steps to do this. This is really a strategy, not necessarily a property or something that involves basically principles about adding or subtracting fractions. This is a, hey, wouldn't this be nice? I can always do this. This is good strategy. Also, they want to note, again, and we've covered this a couple times, if I want to change the sign of a terms in a binomial, trinomial, anything I want, as long as I can multiply it by -1, and it changes this a minus b to b minus a, or really goes -a plus b, right? Which then I can change that to b plus -a, which then I can convert back to a subtraction. of b minus a. So they're showing you that whole process that you go through. Well, why are they doing that now? Because we've introduced this strategy of multiplying by negative ones in a strategic way. So, hey, maybe this works on these kind of situations too. So let's look at this next example. And that's exactly what this is. Hey, I got x minus 7 and 7 minus x. Well, the goal to do the subtraction in this case is to have that common denominator. Well, I can change the order of this or by multiplying by a negative 1. Well, the only thing I can multiply by a 1, is 1, and you get a new fraction that is equal, and I end up with negative 3x over x minus 7. Hey, this is nice. So with one step, when I have this situation, I can create a common denominator. Then I can do this subtraction. I end up with 5x minus a negative 3x all over this common denominator now. So I end up with 5x plus 3x or 8x. Then I check to make sure I can, if I have any way to simplify this. And it is in simplest form. Okay, more examples, more ideas now. Really what they're doing is just introducing more complexity. When you prime factor this one, let's look at a right here, x over x squared minus 25 plus 3 over 5 minus x is, well, you prime factor again, and I end up with the situation where I have x minus 5 times x plus 5. That's difference of squares. I have a binomial. Look for common factors first, none. I have a binomial, is this something squared and this something squared, and there's a difference. Hey, I got difference of squares, factor that. You get this x minus 5 and x plus 5. Then I go, hey, these two are very close. In fact, they're opposites of each other. I could multiply this thing by negative 1 over negative 1, and I'm going to create a less complicated LCD. So that's a good strategy again. So then we have the LCD is really x minus 5 times the quantity x plus 5. So, and then make sure you don't lose your negatives here after I multiply by that. So then once I have this common denominator, because we have to multiply this 1 by x plus 5 or x plus 5, this one has the right denominator, and I end up with this new polynomial right here of negative 2x minus 15 all over this. Then I check to see if I can prime factor that or factor that anymore. If I can't factor it, then I know that at that point I know my fraction's in simplest form. Now they go through some technology stuff here on graphing calculators, which we're not using in the class. So here's another strategy with opposites again. I'm not going to go through that whole thing, but it's very close to the same thing. Is look for these opportunities to change a sign to match up factors, really. And that's pretty good for this section. I'll talk to you later.